We've seen that soils are a major source of carbon dioxide. But what about other greenhouse gases? Carbon dioxide gets a lot of attention, partly because there is more of it in our atmosphere than other greenhouse gases, and also because human activity has had a clear impact on its atmospheric concentration. But there are other trace gases that also contribute greatly to the greenhouse effect and whose cycling has been affected by human activity. The two that we will focus on today are nitrous oxide and methane. Soils can be a major source or sink for both of these gases, depending on the processes at play. And because they are both extremely potent greenhouse gases, even small shifts in their uptake or production in soils can have major implications for climate change. Let's start by learning just a bit about each of these gases and how they interact with the soil. Methane, or CH4, is a long-lived greenhouse gas whose concentration has risen about 150% since 1750. If we look at total radiative forcing of well-mixed greenhouse gases, which doesn't include water vapor, methane now accounts for about 1/5. The increase in methane concentration is due to several factors, including growing numbers of ruminants, the expansion of rice paddy agriculture, and emissions from fossil fuel extraction and use, and landfills and waste. Methane production from soils comes mainly from a process called methanogenesis, which occurs when oxygen is limited and microbes instead use carbon-containing molecules, such as acetic acid or carbon dioxide, as their terminal electron acceptors. The dominant source of methane in soil is from methanogenesis in wetland habitats, but it also takes place in anoxic microsites of otherwise aerated soils. Soils can also take up methane through a process known as methanotrophy. Methanotrophs are prokaryotes that use methane as a source of carbon and energy. Methanotrophy represents a globally significant sink of methane. It's been estimated to account for about 10% of the total sink. Nitrous oxide has the third largest radiative forcing of the anthropogenic greenhouse gases after carbon dioxide and methane. The concentration of nitrous oxide in the atmosphere has risen by about 20% since 1750, mainly due to anthropogenic activities including industry and agriculture. Soils are the largest global source of nitrous oxide emissions, making up about 1/3 of total production. The two main processes that drive nitrous oxide production in soil are nitrification and denitrification. Soils can also take up nitrous oxide, but in general, emissions are larger than uptake, so soils generally act as a net source. It's important to note that they can act as net sinks in some cases, especially in the short term. Now that we know a bit about these gases, let's see how we can measure their fluxes to and from the soil. One common way to measure fluxes of trace gases from the soil is using chambers. We saw an example of a chamber for measuring CO2 in the soil respiration lab. Nitrous oxide and methane measurements follow the same general principles. There are several types of chambers that can be used, which fall under two categories: flow-through and closed chambers. With flow-through chambers, outside air is constantly circulated through the chamber, and the difference in concentration between air entering and leaving the chamber is measured. This is ideal because a constant flow of fresh air assures that a buildup or depletion of the gas of interest will not influence its flux to or from the soil. However, since methane and nitrous oxide are present at such low concentrations, it can be very difficult to measure these tiny changes. For this reason, closed chambers are a popular choice. In a closed chamber, little or no outside air enters the chamber, and gas concentrations build up or are depleted over time. When we learned how to measure soil respiration, we were looking at a closed dynamic chamber where air was circulated in a closed loop between the gas analyzer and the chamber. An even simpler setup, which requires no power and no gas analyzer in the field, is a closed static chamber. With closed static chambers, there's no circulation of gas. The chamber is simply left on for a period of time, and samples are taken periodically. Typically, those samples are taken back to the lab for later analysis. This has the added benefit of making simultaneous sampling more feasible. For example, if you want to sample every 10 minutes over a period of 30 minutes, You can usually sample 5 or 6 chambers at a time, spacing each measurement out by 1 minute. If using a gas analyzer in the field, it is common to only have 1 or 2 instruments, in which case you can only measure 1 or 2 samples at a time, and sampling often takes a full day or more. However, you generally get a more accurate measurement of flux over time from closed dynamic chambers, and it's easy to detect problems like the inhibition of flux due to changes in concentration in the headspace. Let's go to the lab with Paul for a demonstration of a dynamic closed chamber method, and we'll also have a look at how we can measure gas samples that were taken from static closed chambers and brought back to the lab for analysis. Here, we have intact soil cores taken from the field to be used for this demonstration. The gas analyzer shown here can be used this way in the lab, or it can be taken to the field to make measurements in situ. These cores have been contained in PVC piping and sealed on the bottom. Then, a custom chamber has been placed on top with fittings for inlet and outlet tubing going to and from the gas analyzer. This analyzer is a cavity ring-down spectrometer, sometimes also called a cavity ring-down laser absorption spectrometer. You don't need to know exactly how it works, but there are a lot of good explanations available online if you're curious. This instrument can measure several trace gases simultaneously. Here, you see a readout of the carbon dioxide concentration. If you remember from the soil respiration lab, putting the chamber onto the soil can cause a puff of gas, which you can see here. The concentration then increases steadily over time. Here, we have a readout for methane, and after a short period of equilibration, we see a monotonic decrease over time. Note the y-axis has much smaller values than it did for carbon dioxide. This instrument also measures water vapor, which is shown here. This particular instrument doesn't measure nitrous oxide, so for that, Paul uses a benchtop gas chromatograph. A gas chromatograph physically separates gases from a mixed gas sample, such as one you would take from soil, by running the sample through long, winding columns packed with different chemicals. Those chemicals have specific properties that allow them to act as a molecular sieve. By running the sample through these chemicals, different gases are retained to different degrees, and they end up exiting the column at different times. We can then measure their concentrations, and because we know about when each gas should come through, we can assign each peak to a specific gas. If you can't bring a gas analyzer into the field, or if you are using the closed static chamber technique, you can store your samples in airtight vials and bring them to the lab for analysis on a gas chromatograph just like this one. That's all for today's lab. To recap, we learned some basics about nitrous oxide and methane in soils, including why they're important and their primary sources and sinks in soil. We also learned about some of the different methods by which we can measure trace gases and the pros and cons of each. And we saw a demonstration of trace gas measurement in the lab.